So what is image registration? Image registration is bringing together to the same coordinates, to the same space, two images or more. So if we look here, we have an MRI image and a CT image, and we want to bring them to the same coordinates, to the same space. And once we have this, it allows us to do the downstream analysis, like combining the information, comparing the information. It allows for a rich analysis. And this is why image registration is such a crucial step or like pre-processing step in many of the imaging analysis pipelines or imaging visualization pipelines. So what are common needs in research? Why do we need image registration? So just like we saw before, we might have multi-model images that we want to compare. It might be MRI to CT, for instance, but within microscopy, it might be light sheet microscopy to confocal microscopy, for instance, or it might be like even further apart, like light microscopy to electron microscopy. In earth science, it might be satellite images that we don't want to register to each other, but we want to register them to the world map. So we kind of register it to an atlas and not to a different image. And in material science, like there are different properties of materials that are imaged for the same sample, and they look very different from each other. And it creates a really nice challenging image registration need. Another reason that we need registration would be stitching. So if our specimen is too big to fit under the sensor or the camera, then we might want to take the sample in different tiles, like different patches, and then bring them together. Usually stitching is done by, while we image overlapping parts between the tiles, and then we use the information in the overlapping part in order to find where to stitch the images. And today we also have, for instance, microscope tools or other sensors that actually already have this information in the metadata. They know exactly which angle and which position each tile was taken from, and you don't need to rely on the image information to do the stitching. Another need we have is bringing a 3D stack, a 3D volume together. So we might have 2D slices of a 3D volume, and we need to register them together in order to be able to browse through the 3D. And many times, first you need to do stitching of 2D data and then do the stack alignment. And sometimes it's done together in order to optimize and use all of the parameters at the same time. We might have different viewpoints. So maybe it's roughly the same information, or that it shares information, but it was taken from different angles. In microscopy, it might be light sheet microscope that takes the same sample from different angles. But in earth science, for instance, it might be satellite images that not only were taken from different angles, but they might have been taken 10 years apart in different seasons, and the information will be very different and challenging to register. And we can also register temporal information. It might be something like just a video alignment if it's not, sorry, I lost the word. But it might be alignment of different time points that are drifted or are not perfectly aligned, and we need to account for it. All right. So just to understand technically, what do I mean when I say image registration? So I created two synthetic images here, but imagine that they're real images that were taken. To one of them, we're going to call the fixed image, and to the other one, we're going to call the moving image. And we want to move the information in the moving image so that the information, once the two images are one on top of the other, it would perfectly align. This is what we want to do in registration. I just want to have a side note here that if you look at the fixed image here, it kind of looks like the pixels aligned differently with, aligned perfectly with the information that we're looking for. So like we have like just very sharp intensity like for our shapes. But if we look at the moving image, let's say that it was taken from a little bit of a different angle, it also doesn't cover exactly the same field of view because we don't have the plus here. But the information didn't align perfectly with the pixel. This is like, there is never a perfect world of the fixed image actually. And this is why you don't get those sharp pixels. And we're going to get to it in a little bit, why it's important. And then if, again, we look at our fixed and moving images, I just put on top of them like the kind of pixel grid on top of it. And then we want to move the moving image, move the information in order to register the image so that the information would perfectly align with the fixed image. And you can see here that the information in the moving image and the registered don't look exactly the same pixel intensity. And this is because of image interpolation and its needs. So it's because when we moved the sample, it didn't fall perfectly on an integer location of the pixel, and we need to account for it with pixel value interpolation, and we're going to see it soon. All right, so when we talk about transforming, moving the moving image to kind of a different location, we need to understand what kind of transformation types are available to us. And this is maybe the most foundational thing you want to understand about how to do image registration. So the first type of transformation we have is translation. It's the most simple one. You just move the information in the image like a few pixels to the left, to the right, depending on like the axis that you have. So you can move it separately along any axis. In 2D, you would have 2 axes. For rotation, it's just as it sounds. You're rotating the information along 2 or more axes. And scaling, it means that we either upsample or downsample the information, and we can do it separately for each one of our axes. So here we upsampled in X and downsampled in Y. And shearing just means kind of taking the diagonal along a straight line in our image. Then there is also a perspective transformation. And perspective transformation is accounting for the fact that the images were taken at different angles of roughly the same thing. And I think the best way to understand it is when you stand in front of track lines of a train, the track lines that are closer to you would look bigger, and the ones that are further from you will look smaller. But if you look at the same train tracks from above, the lines would roughly look parallel to each other, and this is what you want to account for in perspective transformation. And then there are also local deformations in the images. So there might, like everything we discuss here is globally done for the entire image, but in elastic transformation or local transformations, you kind of want to account for the needed change, like differences in the fixed and moving images in different locations of the images. And you want to account for those. So if we talk only about translation and rotation, those are rigid transformations. And it takes the rigid transformation matrix in order to calculate how we move from the moving image to the registered image. And in order to calculate the rigid transformation matrix, all you need to have is 2 points that you know where you are in the source and 2 points that you know where they are in the destination, and you can calculate the rigid transformation matrix. If you want to add to translation and rotation also scaling and shearing, then you want to calculate the affine transformation matrix, and you need 3 matching points between the images. And then if you also want to account for perspective, it's called the homography matrix, and it takes 4 matching points between the source and the destination that you want to know in order to calculate this matrix. And generally speaking, for elastic transformation, you want to have as many points or information that is shared between the images as possible to account for like transformation in different areas of the images. Okay, So when we talk about like affine transformation matrix or rigid transformation matrix, what does it mean? Like, how do I use it? How do I calculate it, and how do I use it? So for instance, for the affine transformation matrix, this is the example that I have here. I said that I needed 3 points between the source and the registered. So I have XY, XY, XY for the source, and I also have those for the destination. And what I'm trying to do is, if I have those, I can calculate the 6 parameters that make my affine transformation matrix. And once I found those parameters, I can have my affine transformation matrix. And now for every new point that I have in my moving image, like in the original moving image in my source I had with the X and Y, I can plug it in here and I will get the new location of that X and Y. Sorry, X and Y, of course, is if the image is 2D. If it's 3D, you need X, Y, Z, for instance. And you will need more points. 3D is for 3 points is for 2D. And yeah, you will be able to calculate the new location. And this is actually how it's done. For every new location, you would plug it in and find where to take the data from. And if you use something like CV2 or SKImage, this is exactly what they do. They just optimize it so it's a little bit faster than calculating point by point. All right, so it brings me to my next point, which is image interpolation. As we said, nothing promises me that when I go from like my source to my destination location, that the information would fall on an integer location of a pixel. So I have a very simple toy example here. I have an original moving image that is just 2 by 2 pixels. So I have 4 pixels. Each of them has a different pixel intensity. And my destination is a 3 by 3 matrix. So maybe for the edges, it's very easy to see. This would be red, this would be green. But what information do I put in the middle pixel? And for this, I need to do and understand image interpolation. So there are 3 common types of image interpolation, and they're the easiest to understand in 1D, and this is why I put it here. But obviously, images are 2D and more usually. So you can also see it for 2D. So the most simple interpolation is called the nearest neighbor, and it just takes the information of the nearest pixel in the source and puts that information, like that pixel value, in the destination. And I kind of try to simulate it here. So if our new location is the red dot, I just take the pixel that is the closest to it, and 100% of it goes into my new location. For linear interpolation, or if it's 2D, it's called bilinear interpolation. For 2D, you would take the 4 closest pixels from the source, and you will weight them linearly to decide what would be the pixel value in the new location. And then for cubic interpolation, you would use the cubic function, and you would take the 16 closest pixels in order to calculate the new location, and you would weigh them in a way that uses the cubic function. And interestingly, and also kind of surprisingly, the pixels that are more than a pixel apart are actually negatively weighted. But this acts as a kind of edge sharpener, and it creates images that look a lot crisper in the cubic interpolation in comparison to the linear interpolation. But generally speaking, as a rule of thumb for you, linear and cubic produce very, very similar results. And most of the time for speed, linear is enough. I highly recommend to you, when you have that you just take an example image from your data set, see what happened when you do interpolation in linear and in cubic, and decide which one looks better for your data set and your need. Unless your images are really big, and then cubic would take too long to calculate. So I created those weights with this notebook. That you can see how I define like the cubic kernel and the linear kernel, and you can also like use it to understand like how different pixel, if the pixel falls in different location, how the different interpolation types will weigh different pixels. And you can see obviously that the pixel that is that it falls on the most is like the most weighted in all approaches. Yeah, also for the previous slide, you can see how I created it. So I used SKImage and CV2 in order to define my different transformations. And you can play with like different translations and stuff like that and see how it looks in your result. All right. Yeah, so for a general rule of thumb, linear is usually good enough. Nearest neighbor is generally used mostly for binary images, because in binary images, you don't want to change the actual information in the image to have something that is not either the 0 or 1. So you don't want to weigh pixels and get different values than you had in your original image, and nearest neighbor is used for binary images. All right, so let's see a little bit of examples of how interpolation would change our different interpolation types will change our images. I have a very simple source image here. Usually you would never have such low resolution, and thus like the interpolation won't look as bad, but I wanted to like show you the differences. So in nearest neighbor, if I just do rotation on the image or shearing on the image, you see that you only get the original pixel values of the images, and linear interpolation and cubic look very similar, but the cubic does look a little bit sharper. And now I just have a small side note that I want you to remember. Let's say that your moving image is a lot bigger than the fixed image. And that would mean that when you register the image, you would have to downsample the image by a lot to make it a lot smaller. And I want you to remember that in this case, usually you would have to apply anti-aliasing to the image in order to avoid aliasing artifacts in the image. So if you have the original image and you downsample it without doing anti-aliasing, you would have aliasing artifacts where you kind of get those grains in the image, very sharp. And the way to account for it would be to do anti-aliasing. In this case, you would smoothen the image first. So you would blur your image a little bit using something like a Gaussian kernel or a Gaussian filter. And then you're going to apply your downsample. But again, just like choosing the interpolation type, I highly recommend you for your data set to do downsampling with anti-aliasing, without anti-aliasing, and see which one fits your data better. If you want to have the aliasing artifacts, or you want to have an image that is a tiny bit less sharp, but usually for downsampling, it's more accurate. All right, now we're just going to jump into understanding like different image registration techniques, and I divided them into 3 rough categories. So integrated methods would mean that we find the similarities in the images and we estimate the transformation in the same step. It might be iterative steps, but it's done in the same step. Then we have the 2-step methods where we first find similarities between our 2 images, and then we calculate the transformation matrix or the transformations and we apply them. And then the third category would be deep learning based methods, which I would only talk about a little bit. All right, so for the first category, integrated image registration techniques, the most basic and very well known and also used is intensity-based registration, and we're going to talk about it in the next slide. The second one would be mutual information, which is a little bit more robust, but also similar to the intensity-based, and we're going to talk about it later. And there are also other approaches that I'm not going to go into, like the frequency domain method, when we use the Fourier transform in order to calculate our image registration and the transformation. Okay, so for intensity-based, generally intensity-based is used when your images are pretty similar to one another, to each other. Means same modality, you have similar pixel intensities, and I'm first going to just explain the general principle. So I have an original image of Kevin here, and all I did is rotate it by 45 degrees, and I scale it by 1.5. You don't see the scaling here, but you see it here. I scale it by 1.5, and I also added some noise because you would never get a sensor that doesn't produce noise. You would never get two images that are exactly the same intensities. And then if I calculate something like the correlation coefficient to see the similarities between those two images, if I just overlay them one on top of the other, I can also use another similarity metric like the mean square error, for instance. But here I chose the correlation coefficient. I overlay those two images on top of each other, like do correlation coefficient, I get a pretty low correlation coefficient. Now I do the same thing, but instead of rotating by 45 degrees, I rotate it by a lot less, 10 degrees. I only scale it by 1.1. I look at the correlation coefficient, and I got a higher correlation coefficient already. And you can also see that the diff image looks like it has less information in it. I do the same thing, but this time I rotate by only 2 degrees, and I don't scale it at all. I get a much higher correlation coefficient. And if I don't rotate and don't scale, I only have the noise difference between the images. My correlation coefficient got higher. And exactly on this principle, intensity-based approaches work. So now let's say that my original image is my fixed image, and my moving image, the one that I try to bring to the same space, is my rotated by 45 degrees and scaled by 1.5. And now I'm going to iteratively move through the spaces of the possibility. I'm going to rotate the image a bit. I'm going to scale it a bit, translate it a bit, depending on what kind of transformation I want to use, until I find my highest correlation coefficient, and then I know that my images are registered. And if you've been paying attention, you're telling yourself now, oh my God, the amount of possibilities is huge. The search space is too big, and it's true. And this is why you want to use an optimizer, something like a gradient descent, in order to tell you for each one of your transformation, let's say for translation or rotation, if you're going in the, like estimate if you're going in the right direction or not, and using less iterations to find the perfect transformation. But as I said, intensity-based approaches do assume that you have similar pixel values between the images, and this is a very basic registration problem, but you might have like different modalities of your images where the intensity values will not match, even though you have the same information in the image. Let's say that you have an MRI T1 and T2 for the same brain region. For instance, you would have dark in T1 and bright in T2, for instance. Or if you have satellite images from summer and winter, same information, but different colors, for instance. And this is why you want to use a more robust approach, and mutual information is your friend here. I'm going to do a very similar approach in the iteration way of moving the image along the different transformations, but I'm not going to just use a correlation coefficient of the pixel intensity. Instead, I'm going to use the pixel intensity histogram of each one of my images. So for each of my images, the fixed and the moving, I create the histogram of the pixel intensity. Let's say that images are usually between 0 and 255 pixels. For each one of those pixel values, I calculate the frequency of it, and I get the histogram of the image. And then if I take both histograms and I put them in a matrix and compare them, this is called the mutual information matrix. And my point here would be, like my aim here would be to find the matrix that shows me the most structured information. Meaning that I try to lower the entropy. I try to like lower the chaos in the matrix, and the higher the mutual information is, then I know that this is my stopping parameter and that my images are aligned. So this is mutual information. And then let's talk about common tools to use intensity-based or like mutual information and this category of image registration tools. And I recommend ITKElastix for it. This is Python use, but both Elastic and ITK are based on C++. And we will go over a notebook to kind of show you how to use ITKElastix. But I also want to mention ANTS, which is a very popular tool. Even though ITKElastix also offers 3D support, I would say that ANTS is great for 3D data, especially for elastic deformation. It was originally built for brain images, for like MRI images, but you can use it for different data sets. And yeah, it's based on ITKElastix, but especially for local deformations, it has its own algorithms. All right, so let's look at an example of ITKElastix. I'm going to make it a tiny bit bigger. All right. We're going to go over it fast, but you have access to all of those notebooks and you can play with them. Okay, so in this toy tutorial, we're going to see how we use ITKElastix to do rigid transformation. Then we're going to do an affine transformation, and then we're going to do a B-spline. And a B-spline is just an algorithm for accounting for local deformations. So first, I just have helper methods to show me my two images. I have my fixed image and my moving image. I created synthetic data to make it very fast and simple to explain. And if I overlay the images, I see that they don't align well. First, I'm going to show you how to do rigid registration, meaning only translation and rotation. And we need to define different parameters for ITKElastix to decide on how to do the registration. So Euler transform, for instance, for rigid, it's just a type of rigid registration approach. We are going to use the normalized correlation coefficient here. The optimizer is going to be a stochastic gradient descent. So we need to kind of set parameters. Another parameter is like how many times you want to downsample the image in order to calculate the registration. Because if you're going to do it on a full-size image, it's going to take forever. But if you're going to downsample the image, have like simple information, try to register it, then take it from like the registration of the downsample image and then upsample it, it's going to be much faster. And you want to decide on things like step size and how many number of information you have. Step size meaning like how many pixels you move, or how many, and also like how many pixels you sample. You don't actually sample all of the pixels in the image. You define on pixels that are sampled in order to match them, in order to make it faster. And I put those parameters for the rigid. You can have different parameters. And once I define all of my parameters, I try to comment here and explain each parameter well for you. And I'm going to apply the registration, and I'm going to look at my images. So before this was the overlay, and now the overlay look a bit better, not a lot better, but again, it's rigid. It's only rotation and translation. And then when I look at the diff that I got, I see that I got better. Now, if we're going to do a affine transformation, generally, the parameters are pretty similar to the rigid. They might be a bit different, but if we're applying an affine transformation, then already we see that our overlay of the images looks pretty good. Also, our diff looks pretty good. But then if we're also going to do on top of an affine, we're going to do B-spline, which accounts for local deformation. Then if we look at our results, and especially if we look at the diff, we see that we practically, like we almost don't see differences between the images. So in this case, we didn't have to account for local deformations in order to get the best alignment. Very important to note that you never do the local deformation, elastic deformation before you bring your images to roughly the same space. So you always have to do rigid, affine, or perspective, and then to account for local deformation. So it's always 2 steps unless your images are already roughly aligned. Oh, sorry. There is also in this example how to use the 3D in ITKElastix, and also just their they have a lot of example notebooks and they have good documentation if you want to use that tool. All right, moving on to other techniques. So the two-step techniques, generally the first step would be detecting similarities between the images. And then the second step would be using those points of similarity to estimate the transformations and then apply the transformation. And there are a few ways of detecting features in images or like similarities between images. One of them would be feature-based approaches. There are classic approaches that actually work super well. I highly recommend them. That would be SIFT, for instance. It's the most robust one. Orb would be like a faster one, but they're very similar. Another way would be like segmentation-based registration. So let's say, sorry, we're going to look at a SIFT example in the next slide. Another one would be segmentation-based registration. So let's say that you have objects in your images that are already segmented. So you already have like labels of those, or that is really easy to produce the segmentation. You can just use the segmentation and register them, and then register your images based on the same transformation if it's easier. There is also model fitting that we're going to look at an example of in the next slides. And here you don't automatically detect the feature as much as you first decide what are the features. You want to bake in some information that you know about your images, about your features. You want to define which features to find and then find them. And in graph-based model, it's also very similar, but there might be a relationship between the location, for instance, of your features, and you want to bake it in as well. And we're going to look at an example of this soon. And yeah, of course, once you found and match your features between your moving and fixed image, then you can estimate your transformation and apply it. So let's try to understand a tiny bit of how SIFT works. So the first thing that SIFT does is try to find features of the image and to match them between the images. So here I have two images from the local bouldering gym that I go to, and we just look at the same route. It's the same location on the wall, but I took an image of it from two different angles. And then the first things that SIFT does is find in each one of the images separately features that are salient in the image. So what are features? Features are usually edges of places, or again, things that are very, very salient in the image. So for each one of the locations that it detected, in this case, this is the black circles. So for each one of the black circles that it found as a feature, it has its location, it has the key point itself, and it also has a descriptor of this feature, which means it's a feature vector that explains what we see here. What do we see in this location of the image? And then it uses each one of those features and tries to match which feature vector of each location looks the most similar to a feature in the second image. And this is what you see here as the lines. Like SIFT found that this location is the most similar to this location in the image. And you can see here that it actually found like there are some mistakes here, but most of them are correct. And once we found enough points in order to like do a fine transformation, we only need 3 points that are matched here and here in order to calculate an affine transformation matrix, and we can apply it on the moving image and register it to the other image. So let's look at an example of how we actually can use SIFT. All right. So here I use SKImage, but you can also use, for instance, CV2 in Python. First, I just define, again, my images, I import them, and I look at them. In this case, my images actually look very different to each other. It's because it's taken from different modalities. You can see that the colors don't actually really match, or like And also, it's not the same slice of the image. It's two consecutive slices, so the information is not exactly the same information between the images. And you can also see that the scaling is different. I put it on the axis here. So it's not the most straightforward registration problem. Then I just define some functions that I will use later to use SIFT. I define my SIFT detector. Again, this is SKImage, but you can also do it in CV2. In SKImage, you can't define the parameters of SIFT, but if you use CV2, then you can play with different parameters and not just use the default parameters of SIFT. And it's going to be a bit too much for me to explain how SIFT work in details in this workshop, but you in order to roughly understand, SIFT kind of downsample your images to different resolutions and does a difference of Gaussians between the two different resolutions. And if you do a difference of Gaussians, it means that you apply a Gaussian filter on each one of the resolutions, and then you do a minus between the difference of Gaussians, and then you can kind of it actually acts as an edge detector, a feature detector in your images, and this is how SIFT finds information that is relevant in the images. And then for each one of the key points that SIFT found, each one of our feature, it defines it as the location. This is the key point, like the X and Y for 2D information. And it also defines a feature vector, the descriptor for each one of the points. And this is just like what information I have, let's say in the, I don't know, 5 by 5 pixels around that point, or maybe a bit more. All right, so I used SIFT on each image individually to find the key points and their descriptors. And then I also try to match those, the feature vector of each one of the features in order to see which one of the feature vectors is the closest to each other between my images. And doing this, I get the matches, and I also wanted to plot them and see what kind of features I got. So I plotted my matches, and it doesn't look amazing here. There are some features that are matched. I think we see it here a bit better. So like 0 and 0 match, but I would say that 1 and 1 is not in the correct location, something like that. It doesn't look amazing. And then, but we still try to give it a shot and try to register to find the homography matrix using, we need 4 of those points to find the homography matrix. Again, there is a side note here that is important. You can use RANSAC. This is a different algorithm in order to decide which of your points are better together, and which of your points geometrically make sense together, and which of your points you want to like throw away and they don't match each other. This is the RANSAC algorithm. So you can use the RANSAC when you find the homography matrix to only use, like to choose the best 4 points that you want to use. And this would give you the warping matrix, the homography matrix in order to warp your images. And then you can warp your moving image using that transformation matrix. And we can see the results of which actual points RANSAC chose. And again, it doesn't look amazing here because kind of garbage in, garbage out. RANSAC got really, really bad points, so it couldn't find good points. And then when we actually try to warp our image using this transformation matrix, we don't get a warped image correctly, like a correct image. So I know what went wrong here. We have different modalities. It's not the same information because it's not the same slide. We need to give SIFT a better chance to work. And in order to do this, I chose to just do one small pre-processing step on each one of my images. And I normalize the pixel value by rescaling the intensity. This is an SKImage function. And once I did that, maybe you don't see the difference a lot here, but actually I made my pixel intensity values make the feature pop a little bit more. And I start from those images now. I repeat the process. I got more key points here. A lot of them still look wrong, but I also have a lot more that are correct. And using this, it gave Ransack a good chance to see which points actually match each other geometrically well. I only got 7 points here that match, but they match perfectly after Ransack. And we only need 4 points to calculate the homography matrix, and thus we got images that were registered correctly. And I also looked at the mean distance between the source and the destination of all of my points. I only used 4 of the points for the registration, but I had 7 points, and I can look at their distance and to kind of try to estimate how good, how accurate my registration is. And kind of knowing that this worked, I just want to see if maybe I can even improve it, or is there a better way to find key points. So another pre-processing step that I did here, instead of using the rescale of the intensity, is I rescale the intensity in a different way that is called histogram equalization. And then I got those 2 images, and while they look super ugly, they actually make the features of the image pop even better. I got a lot more key points. A lot of them are better. And then I know that I have a very robust estimation of if my transformation was well or not. I can use a lot more key points, and I can register the images. But then you can tell me, but I didn't want to register an image that I already pre-processed. I wanted to register my original image, but that's not a problem, because the way that we did it here is we found the homography matrix. We already have the homography matrix, and now we can use any image that came from the original moving space, use the registration matrix, and warp any image that we want. We can also do it for images that are downscaled or upscaled, like bigger images or smaller images, as long as they came from the same space, and that's the only difference between them. But it does demand another step in the middle. So you just need to remember it's possible. And in the notes of this presentation, you can see the extra step that you need to take in order to do so. All right, so this is how SIFT or generally how feature, many of the features detection approaches work. And now I'm going to show you a different approach that also uses features of the image. This is actually taken from my PhD thesis. So we had a problem when we had tons of Drosophila wings that we had to first register together in order to start our analysis. So the way that we decided to do, and the wings were in very, very different orientation to each other. So it might be flipped, it might be rotated. We had many, like, I think hundreds of thousands of wings to register. And our approach was to decide on 14 locations. Those are the blue marks on the wings that are on the veins of the wings, where we manually annotated, and we only needed like 20 annotations of those. It took us less than a day to annotate 20 wings. And then we also added more landmarks, more features that we wanted to detect just by having them in equal locations between the features that we manually selected on the veins. And once we had this, we actually just used a CNN, a convolutional neural network, in order to detect those locations on each one of the wings. And once we have those locations, as I said, we first applied an affine transformation. So we used 3 of those points to bring it to roughly the same location. And then we also used all of our landmarks in order to use thin plate spline, TPS, to account for local deformation between the wings. So we use those 2 steps, and it really wasn't a lot of work for kind of a sophisticated, nice registration. All right, which like that method was kind of a hybrid. We used deep learning in the middle to find our landmarks. But let's talk about pure deep learning approaches. So interestingly, for image registration, deep learning is not the king. And usually when it comes to vision, a lot of people think that like in a lot of vision tasks, deep learning is the best approach, and it kind of solves many problems. In image registration, the classic approaches still are used very, very commonly, even though deep learning has good approaches that work. Many times, deep learning approaches do require bigger data sets because they need to train on your specific data set in order to work. And the user level is kind of intermediate. You're expected to like know Python and maybe like be able to like understand a little bit how to maybe use even PyTorch or TensorFlow, or at least how to install them. Those are deep learning libraries. But deep learning approaches do have the advantage that usually they're very, very fast to maybe not necessarily to train, but to predict on your image the deformations that are needed. And they're many times very good for very complex registration needs because they can find like local deformations in your images very well. So one approach that I want to, or one tool that I want to mention is voxelomorph. And in voxelomorph, it's a really nice approach because you don't need training data. You don't need to actually have a moving image and the registered image pair. All you have to do is to have enough pairs of the fixed image, and the moving image. And those would train on your image data set to train a convolutional neural network. And the output would be kind of the deformation fields, meaning a map that shows you where every pixel should move to in your pair. And it does that by trying to minimize the similarity loss between those 2 images, so to find the transformation that makes those images the most similar, together with a regularization term that tries to make this deformation field smooth. So kind of try to think about it is trying to make a sensible transformation here that doesn't like look too wiggly or something like that, where every pixel moves. So as I said, it's super nice because it's unsupervised. You don't need to actually have registered images. You just have to have enough pairs to register, or if you have like images that came from MRI, maybe they already have good pre-trained models for you. You can also use a semi-supervised approach here if you already have anatomical labels for some of your images. If you have like segmentation and stuff like that, you can use that, and it would maybe train faster or give you better results. And it offers both affine and elastic registration. So you can first do an affine transformation and then do elastic deformations. And as I said, it's very fast, and it has an advantage that not many deep learning approaches have, where it's highly interpretable, because you actually get like your result is the deformation fields of how to move the images, and you can easily see if it's correct or not. All right. So we talked about different types of algorithms and approaches to do image registration. And now let's just talk about like how we choose our approaches, what are our considerations, what are our challenges. So first, I would say that you want to select the correct methods, like the correct approach for both your data set and for your downstream analysis. So if your images are multi-model, probably intensity-based won't work, but maybe mutual information would work. If they're even more different to each other, maybe you want to use a feature-based approach and stuff like that. And then you need to consider the transformation type. And this is really important. So as I said, it's super important to first bring the images to roughly the same coordinates and only then account for local deformation. So you first do something like affine, and then you decide on a local deformation approach. But also, it's really important to know that if your image only has global deformation between the images, only needs global registration, and it doesn't, you don't have local deformations in your images. If you're gonna do local deformation, you're gonna introduce errors to your registration. So you need to know kind of what deformation exists in your images in order to decide on the best approach. If you're going to use a perspective transformation when you only have a fine transformation between your source and your between your fixed and your moving image, you're actually going to introduce errors, because every additional transformation that you do always introduce a little bit of errors as well. And then another consideration is maybe you want to do a little bit of pre-processing on your images before you do your transformation and your registration. So maybe if you denoise your images before you do the registration, you can detect similarities and features in the images much better. Maybe you want to correct for intensity, like we saw in the SIFT example. You can do equalize your histogram and stuff like that to make your features pop. Maybe you want to rescale your images, meaning upsampling or downsampling, making the images bigger or smaller before you do the registration. So if your moving image, for instance, is much bigger than your fixed image, maybe you want to rescale the image first, make them roughly the same size, meaning that the features are the same size and what you're looking for. And then the registration task would be much easier for many of the algorithms. Or maybe you even want to apply different filters of your image and do the registration in that space. And this is a really nice example of it. I took it from this YouTube video. I really liked it. So if you have a CT image and an MRI image, they look very different. And the MRI image has so many features that are irrelevant for the registration task. But if you're going to apply an edge detector, meaning that you apply a filter on your images to find edges, then you might end up with those two images that, while maybe are irrelevant for your downstream analysis, but for the registration task, those two images would be much more straightforward to align. You do the first global transition or like registration on those two images, then you can maybe use the more complex images for local deformation, maybe yes, maybe not. And then your downstream analysis are made once you registered those two images to each other. All right. So let me try to give you a tiny bit of guideline of, okay, I need to register images. How do I choose my approach? What is my pipeline? Okay, first question that you ask is like, how similar are my images? Do I need to pre-process them? And if I can find a good pre-processing step to make the features or the similarities between the images pop, if yes, you do that. You might correct for intensity, resize. You might want to segment things in your images and use the segmentation for registration. Or maybe your registration is a bit more straightforward and you don't need to do it. Then the next step is maybe you have the expertise, you have GPUs, computational resources, and you have enough training data, you have a big enough sample of moving and fixed pair images in order to apply a deep learning approach. And this makes it super easy if you have this expertise, and you might just want to do voxel morph on your images and finish there. But if not, then you have to ask yourself, how similar are the images that I want to register now? If they're very similar, intensity-based registration, something like using the cross correlation, using ITKElastix will do the job. If they're somehow similar, maybe you want to use like histogram-based, like the mutual information. And if they're not very similar, using feature-based methods would usually get better results. And if your images are not at all similar and you won't be able to do good registration based on your images, unfortunately, maybe you have to retake your images. And there are a few ways of doing it. Either you need to improve the quality of the images to have features and similarities between your images, or you need to use external information within your images that didn't come from your sample that would facilitate your registration. What does it mean? So in microscopy, for instance, people use beads that they put on the slide next to their sample. And then you would see the beads once you want to register the images in both angles, if it came from like light sheet microscopy, or if you took the same slide and you put it in two different sensors, like in two different microscopes, then you will be able to find those external beads, use those 3 of those beads for a fine transformation, and then continue your registration from there. Yeah, okay, so now once you chose your approach, obviously for a feature base, you might want to decide if you were doing model base or like more classic feature base. You want to if you want to bake in some information, you want to engineer your feature, or you want to do a more automatic approach, for instance. Yeah, so once I chose my method, I also need to understand what kind of transformations I have in my images. If the images start from a very different location from one another and are not roughly aligned, I will first account for local deformations. So I will calculate a region, affine, or perspective transformation. And once I did this, are there also local deformations that I want to account for? If yes, I would use something like TPS or a B-spline, or ANTS has its own approach, accounting for local deformations, and I will account for those. And then if there are more images in my sample that came from the same coordinates, from the same space as the moving, I can also apply the same transformation that I did on those images. This is very common, for instance, if you have different channels of the same image, you would only do calculate the registration on one of the channels, and then you would apply it for the rest of your channels. You don't need to recalculate it. All right. So just to summarize on some of them, we already talked about those software tools, but I just want to mention here the most common software that people use for image registration. So if you come from the field of like biology, microscopy, and stuff like this, and you don't have any programming experience, there are plugins that are pre-installed or that you will need to install in Fiji that will facilitate your registration. Those are generally found under the plugins and in the feature detection or registration, and you can see like examples here. The common Python libraries, CV2 is super strong. It has many features. It's written in C++, but there is a Python wrapper, or SKImage. ITKElastix, we saw an example of it. It also works in 3D, and it's generally for like intensity-based or mutual information approaches and those kind of iterative approaches. We mention ANTS, especially for neuroscience images, but also just generally you can apply it for 3D, especially when you have local deformations. Voxel morph is the approach that we talked, that is deep learning, that I think is the most commonly used. Super nice because you don't need your training data to actually have the result in registration. So it's unsupervised. it's a Python tool, and they have a TensorFlow and a PyTorch version. And I didn't mention it, but Deep Lab Cut, if you want to kind of engineer your features and you want to like define like spatial locations of your features, it uses something. It's solving pose estimation, and even though it's a Python tool, it's super straightforward to use. It's very fast, works really well. I highly recommend it if those are your issues, and if you want to do like registration and tracking. Each one of those is a link. You can open the the presentation and get to those tools. And if I'm allowed to do a little bit of a self-promotion, there is Voltron, which is an R package with a really nice shiny app, meaning that it has nice GUI to lead you through the registration. It also allows for some pre-processing steps. It's written by Artur, my colleague, and it is based on the SIFT-based image registration Python package that I wrote that you can also use. It's a command line tool. Yeah, and this is all. Thank you so much for your attention, and I'm looking forward to